Good morning, everyone. Nice to find you back today for the second day of our utility scale storage technology web conference. Let's have a look on the program of today. Today is a program of 2.5 hours. First program will be introduced with intervention about the role of energy storage system for integration of renewable in the grid. After this first moment, the event will continue with several focus on issues that are of first importance for TSO, with two speakers who will share their experience of the TSO about connection to the grid, control automation, and fast reserve. So it is a 2.5 hour program, very interesting. As yesterday, in terms of a question answer, you can use the chat to use a question if you have, and to give opportunity for the speaker to answer. That is the organization of today. So coming back to the first presentation, it's a pleasure today to welcome Claire, Mrs. Claire Lajoie-Magin from RTE for presentation of energy storage system for integration of renewable in the grid. Claire, floor is yours.
Thank you, Emmanuel. Okay, so back to the slide, if possible. So to introduce myself, I will just say that I am a scientific advisor in RTE, the French TSO, and apart from my mission in RTE, I am as well president of the IEEE France section. I'm a European expert for storage and a member of the executive board of the European Association for Storage of Energy EASE. So today I've prepared a very basic presentation, and I would like to apologize because I know that you are all much more experts than I in electrical system. But I would like to point out some very basic points and to illustrate this issue of flexibility. What are we talking about when we are talking about flexibility and the role of storage, and probably to put it in the right place and tell some wrong and right ideas about storage. So first of all, so very basic points. First slide, please. Is it possible to change the slide? Yes. So we can go directly. Yes. So flexibility, of course, you know that it's a basis of our electrical system, because the frequency, which is a very, very fundamental key issue, is in fact the result of a very difficult balance between demand and generation, and which is not so obvious. So we have, in fact, a lot of mechanisms. Some of them are completely natural, like synchronism, because it's, of course, you know, just the speed of the rotating machine, or the inertial response, which is as well ensured completely naturally by the rotating masses. And for the other kind of flexibility levers, we need some devices, equipment, and even market structure to be sure that we will be able to maintain this very fundamental balance and keep the frequency in the range where it has to be. Next slide, please. So when we look at the load, we can see that, of course, the load have a very variable form. And we have a very interesting studies, part of the PhD thesis, which decompose this variation in several time scale, from the daily variation, the weekly variation, and the annual variation as well. And it is very interesting to see that these variations are very different and correspond to different mechanisms. So, of course, as I previously said, flexibility is completely fundamental. It's the ability of the power system to cope with this variation from the real time up to, of course, several years. This variation can be just predictable, and others are completely unpredictable. And we can decompose them with the load variation that can be managed with several levers like demand-side management, or even the tariff structures that can have some impact on the way of consumption will consume electricity. Of course, in the same way, we have for the generation in the different time scale different levers to adapt the electricity generated, produced. And for the network, it's the same. We have some very real-time response, and other need a little more time and can be used. For example, if I take the example of maintenance, we can choose the period of the year where we will choose to disenergize some lines or some substation to perform the maintenance. And we have also the investment lever. It can be for generation, for network, and even for storage, but it needs much more times, of course, to adapt. And if we have a look in the storage, sorry, but this slide is not so up to date, and we can probably change a little, because of course between batteries and flywheels it's not exactly the same time scale, but we have as well, and we don't have to forget that the pump storage is still today the most used storage lever. And we have some other more advanced but still very experimental one, like the compressor storage. And we are more and more talking about the use of power to gas as another lever that could be used for yearly and more than yearly way of store energy. When we look more precisely about flexibility, it's very interesting to note that today, if we decompose them between daily, weekly, and annual modulation, between the different levers currently used in the French network, in the annual and weekly modulation, it's above all the nuclear, the interconnectors, and a little less pump storage that are used. So nuclear and interconnectors are the more used lever for this annual and weekly modulation. And if we look at the daily modulation, then it's in France the demand-side management, and behind this demand-side management, it is a very simple and easy to use tariff structure with the domestic heaters that allows and in a very economical way to have this very huge and useful daily modulation. Another view that illustrates the same point, and we see for each of these levers, the nuclear, the hydropower, the gas, coal, fuel, biomass, interconnection, pumped, or the demand side management, which are used and in which time scale from the annual, weekly, or daily one. So it's just another vision of the same real data for the 2015 year. So it is well known that we will need more flexibility tomorrow. This need is increasing because of the renewable, non-dispatchable generation plant. But how many? It's what I would like to show you. We made some simulation in the next slide. Oh, they were an animation, but it seems that it's not dispatch. That's a pity. Perhaps if you change the slide, perhaps we will see it. No, it's a pity. So back to the in this slide, and I hope that it will be sent to you all attendees, because we could have seen that this impact is of course increasing when the level of the solar of wind farm is increasing. So this is when we have no solar, 0% or zero windmill. And if we have up to 50%, then we would have seen, and I hope that you will see them, this need that will increase dramatically. So sorry for the animation that was lost in this vision. Another study that was done in the French context was to try to have a vision of what would be needed in 2035 according to different mixed generation scenarios that are called ampere and volt, and that are described in the side of the slide. So we can see, and it's very interesting to note that, of course, the need is increasing, but not so much that sometimes it is said. So both for the annual, weekly, or daily time scale and power on energy requirement, we will need more, but the increase in this time scale 2035 is not so big that it is often said. So, to finish, to perhaps upset you, sometimes we hear that if we put a storage plant close to a viable renewable plant, then we have a dispatchable one. So is it the solution? Is it the key for our network of the future? And of course, I have a very more balanced answer. And I would like to illustrate that for me it's just a lever amongst others, because we already have a lot of levers that will keep being very, very useful and economical one, and that we have to not forget them. And if we have a look, sorry, it's in French, but in the right side, this effect of interconnection, the European interconnection, if we imagine, of course, it's a kind of dream. If the interconnection was perfect, we would have a reduction by almost 30% of the need of flexibility. So just connecting grids can reduce this need of flexibility. The other point that seems to me very important is that we have to not and never forget that storage, whatever the technology is, and of course battery, and this slide is for battery, has in itself a significant effect because we use raw materials, it generates losses. So don't forget that if we have more renewable power plant, it is for environmental issue. So we have to take this into account when we choose to have a storage plant to not lose some electricity produced by the renewable. And last part is that a storage does not solve alone all the issue. Of course, if we dimension correctly a storage system, it can make a variable renewable plant dispatchable, but never a synchronous one. Last slide. So I am not saying that storage is not a good solution, and it has indeed a very important role to play in electrical system. And we are almost every month discovering new services that it can offer to the grid. So it's a very important part that we need to correctly know, understand, and use each time. That is the most interesting one. So if I want to sum up, and what I would like for you to keep in mind is, first of all, transmission system operator need to better know just electricity and energy storage system. First of all, to adapt correctly the requirements for the connection and access to the market. Just an example, sometimes it is said that storage would be not charged because it can produce services and it is anti-cycling. In fact, in itself, it is not anti-cycling at all. It is a service that can be anti-cycling. It can help to cope with congestion, but in some case, it just generates other flow. So it's very important for TSO to well know and separate the technology in itself and the use of it. Second reason, very important, is if you want to use it very correctly, you need to know what is possible and impossible. And for example, if you want to use a storage system to cope with and reduce congestion, so you will have to take into account the fact that, for example, if you want to absorb some excess energy, that means that at a time you will need to discharge the storage system for him to be ready to be charged by this amount of electricity you will need to put in. So for all of that, you need to know it correctly. And last reason is, as I was saying, we are still discovering new possibility, new capability of this storage system for the benefit of the grid. So we need to understand them and at the best of the performance, and not to limit them behind this performance. But, and it's the last part of my presentation, never forget that it can exist best environmental solution, for example, the demand-side management, which is very often a very smart and very cheap system.
Thank you, Peter.
Okay, ready for some question? If
there are two questions actually.
Yep.
One from our Egyptian colleagues. They ask if it is a good choice to combine storage with renewable energy projects.
Yes, in fact, it can be. But what I was saying is more often, instead of putting a storage system close to the renewable non-dispatchable system, it is very often better to mutualize it in the grid, because in final you will need less, because of course you will smoothen the need, and you will use this natural smoothing between the grid. But sometimes it is not possible, just because we have not the grid. Just what I was trying to show you by this small example is there's no universal solution. Each time it is better really to study different solution and to choose the best amongst a set of them.
Okay. There are two other questions. How to consider storage to be placed correctly in case of high penetration of renewable energy?
Sorry, I didn't catch it.
How to consider storage to be placed correctly in case of high penetration of renewable energy?
I'm not sure to understand this question correctly, but yes, of course. I wasn't saying, of course, that it will not be useful. Of course, it will be useful, but just to not to forget other solution and to combine different solution, grid and storage, storage and demand-side management.
Okay.
And sometimes it can be better not to use all the excess of energy if the environmental impact is better in this way. It depends.
Okay. And there is the last question regarding how do you assess the need of flexibility? Concretely, what parameters used to evaluate this concept?
I think there's no real tool to assess, but what was used in the studies that I show you some figures and some result. In fact, the real shape of the load and the regeneration, and the tool was simply a timescale decomposition between the daily, the weekly, and the annual that allow us to put these figures, but it's just how we say that you know perfectly that if you want a short time and you have performed already the study, and you know, for example, that only storage is the key between battery and power to gas. Battery is okay today for up to some hours, but after some hours, it is so large amount of batteries that it becomes completely unfriendly. Environmental and economically speaking, it's very difficult, and perhaps other solution are needed. But I don't know some tools.
Okay. Thank you.
Thank you very much, Claire.
Yes. Just a last point, perhaps, because I'm not sure, but I see a question about dispatchable and a synchronous question. And later in the afternoon, my colleague Florent Xavier will talk to you about the grid forming and probably will explain much more in detail this difference between inertia and grid forming.
Yeah, it is a perfect move to the next presentation. If you allow me, we have the animated presentation. Luca, if you give me the floor, we can have a look on.
Oh yes, it would be nice. Yes,
yes,
because
I
I think it's very impressive. Yes,
I can do it.
Yes, because of course I say it's not a so huge impact, but it has a real impact. So
Do you
it's very
see it?
interesting. Yes, but still not the animation, but we see the slide.
Okay, animation is on my screen.
It is not.
Not in yours.
No, it is just the 0% vision that
Okay,
it is
and
displayed.
not 10 and
Not 10 and
okay. So perhaps it's a problem with the tool. What we can do is to share the PDF version with attendees.
in the PDF, I fear that it.
Sorry, in the
Yes.
PowerPoint version.
Yes, the PowerPoint version. Yes. I allow you to do it because it's a pity not to have seen it.
Yes, it's a problem with the tool. I'm sorry.
But in fact, this slide shows that it has really an impact, but the following slide show this real impact is not as huge as often said.
Yeah.
Let me check with you can see it.
Yeah.
Oh, yes. Nice. Thank you. So now you can see it perfectly.
Okay.
So this is the net load. That is the load minus the rest generation. So we can see that in the case of the solar, it's in the daily time scale. Of course, we have a lot of figure like that, and I choose the more impressive one. So for the solar generation, it's in the daily time scale that we see this increase. And for the wind generation, it is the annual time scale that show the highest variation between 0 and, I don't remember, it's 15 or 16%, 15, from 0 to 50%. So,
okay.
Thanks.
Thank you very much, Claire.
You're welcome. Hope you enjoy.
For sure. Great. Thank you very much.
So, I have to leave you, so have a nice.
Okay, thank you very much.
Bye.
Bye, thank you.
Florian, I guess you are connected?
Yes, hello everybody. Yeah, I'm connected, and thanks, Claire, for the introduction on one part of my presentation.
Yes, of course, they are a little linked. Nice presentation. Bye.
Bye.
So yes, I will continue with the this afternoon workshop. Thanks for the invitation, and I have joined the two parts, the one on the connection to the world network and another part on Zoom on control and automation. Before that, just sorry for the inconvenience. My son is at home today. I have some trouble because my wife has some symptoms of COVID, so I'm obliged to stay at home today. And maybe you can hear my son several times. So sorry for the disturbance. but I will try to present without noise. So first of all, I will introduce me. So I'm Florent Xavier. I'm working in the R&D division of RT, and I'm the manager of the group integration of new technologies. I will my camera. So in my team, there are two parts. One on the question of system stability, and we are involving on some European projects like Migrate and Osmosis, and I will speak about that during my presentation. And we are working on the question of how to operate a system without synchronous machines, or what are the solutions for the system with 100% power electronic devices. That's one part of my day, and the second part are developed some simulation tools, some open source simulation tools, for the in order to study and the system stability with massive integration of P devices. In a few words, so before starting my presentation, in a few words, RTE, I don't know if everybody knows, but is the French transmission system operator. We are owner of our asset, and we operate the system. So we are there are more than 100 kilometers of transmission line in our network. RT's network is the biggest in the European network. Networks, we operate the system with 8 control centers, and we are linked with the regional coordination center, which are called. So that's a few words about RT. And can go to the next slide. So, in order to during this next 1 hour and a half, I structure my presentation with 4 parts. One about the evolution of power systems. It's just a large introduction about our system. Then the second part is about the regulatory part, and an overview of the French regulation on storage capacity. Then the third part is about the market access for storage. And the main part of my presentation, and where I'm more easier, is about the technical applications. And I have several applications that I will mention during this presentation. One about the congestion, the other about the dynamic uses, the frequency control, or the frequency deviation, deterministic frequency deviation. And the last point, and nonetheless, about the grid farming controls. Go to the next slide. So today, we observe a huge increase of the system complexity. Our system at the beginning, today is an electromechanical system with synchronous machines. But now, with the integration of renewable energies, which are connected on the network via power electronic devices, there is a lot of changement and modification on the network, and we observe a transition phase between an electromechanical system to electronical systems. And main of the devices which are connected to our system today are connected via power electronic devices today. So that's the first point. Second is the impact of this renewable energy. And that's what we can see today is the decrease of inertia, not in continental Europe network because it's a large network, but in some island, like Ireland or Great Britain or other countries, we started to see the impact of the decrease of inertia in our system. So that need faster dynamics, but other solution like storage. Then the two others modification are about the loads. At the beginning, loads was stagnant, but now with electric mobility, it will change the operation of our systems. And the last, but not least part, the number of stakeholders, right? And it was increasing a lot, and there are many impacts in order to operate the system. So there is these four main points, but what we can see is a digitalization of our network. And if you go to the next slide, this figure is just here to complete my previous slide. We can conclude that the electricity sector will go more changes in the next few years than what we observed in the last 50 years. With new users, electric mobility, new consumption, renewable energy source development, and a lot of uncertainties on deployment rate solution. So if you go directly to the storage unit, which can play an important role in our future's system with massive integration of renewable energy. Few words before starting about the connection of storage. In France, in our RT, there are no regulatory framework about storage connection, batteries connection, because for hydraulic storage, there are already the code and requirements. But for storage unit, if you look at the network code, the European network code, nothing are mentioned in the requirement for generator or in the demand connection code. The two codes linked to the producer, to the generation unit and for the consumers. And this is a point that in European we have to solve in the next years. But in each country, there are some specification and requirements to identify the storage unit and the connect. And what we have to coherent in our network is to offer the same treatment for every grid users in a similar situation. That's why we have to give requirements and deep capabilities to connect storage unit on our networks. So next slide, please. So there are different connection opportunities in our network. Here I will mention three connections. The direct connection to the TSO networks. So we can offer a direct point of connection or point of common coupling in an effort to install the storage or the batteries on the high voltage network. Sorry for the slides were in French, the figures, but I don't have enough time to change that. That's the first connection opportunity. The second is about the indirect connection. We offer today's, and we propose a connection for a generation unit, and it's possible for producer to combine the production unit with the storage capacities. So it's a second solution in order to connect batteries. And the last point is to connect directly as a consumers, and I call that indirect connection. And we the installation can connect directly on the distribution networks. The next slide. So about the procedure for connecting generator or storage unit, today we have defined a version with requirement, and the link is on the slide, in order to connect generators. And we use this kind of requirements for batteries or storage units. And the procedure defines the main step of connection, the different agreement exchange between RT and the customers or the producer, the information about the network capability, because we need this and this information in order to connect, and the location of the connection. And the last point is about the contractual relationship between RT and the customer. If you go to the next slide, I have a scheme to give you the different phase of connection in our RT network. The first stage is a study phase, in order to define the different interface between the storage unit and RT. The second point is about the studies needed and the work needed in order to connect the unit. And then the cost, of course, because we can make studies and we will define, thanks to these studies and the interface specification, what are the costs of this connection and the time needed for this connection. And when we define that, and after validation, we go to the work phase for building the connection. And usually that's the connection is built by a company working for RT. And then the last phase is when we install the material on the network, is the qualification phase. It's a seat acceptance test, for example. In order to test the storage unit based on this requirement that we define on the first phase, we check all this requirement, and then we give the certificate in order to provide power or consume power on our network. If you go to the about the main connection steps, that's a chronological phrase key which gives you the different timeline for the connection. So first point is entering the queue. So we propose the connection, and that's that's called in French PTF, acceptance. And we need between 3 and 6 months in order to give the connection agreement. And the first step about the technical design specification or the telecontrol specification. That's the point that I mentioned in the previous slide. And then we have the studies period into 1 or 3 months, and the connection agreement go further, and we have the work phase between 5 and I don't know. It depends on the lot in the infrastructure and the topology of the network in order to define how long this period can take. And the last point is the test period with the energization, the first energy transfer, and the final commissioning. So it gives you an overview on the main connection step on RT network. This figure and this different step can apply to a generation unit owner and for HVDC connection and for different all kind of connection on the network. Next slide, it's just to precise in detail what is in the previous slide, what is inside the different connection, but it's not very important. If you go about the technical specification from RT, just a small point, there is a performance specification about the voltage control, frequency control, the steady state behavior, or black start file copy. Another about the telecontrol specification for active or reactive power measurement, voltage at the connection point. This point is very important because we need telecontrol and this telecommunication in order to ensure our system stability or to control voltage or frequency. The counting specification is here in order to participate on ancillary services, EMA rules, or all kind of markets, and in order to define the payment. And the last point, it's about the protection system specification, because we need to protect each system which are connected on our network. Next slide. So if you go you know that how to connect on the network and the different phases to connect on the RT network, now we will go further about the overview on the French regulation and French legislation and regulation on storage. As I mentioned at the beginning, storage is not explicitly defined in the French legislation. There are few provisions that are storage specific in the French legislation about tariffs and about the energy climate bills, but everything is not totally defined. That's the main thing. You have to know that the ministerial order will soon be released in order to clarify the condition about storage which are eligible to support scheme. And today, RT is currently contributing to transmission of the directive on common rules for the internal market. And if you go to the next slide, you have to know that RT and France has targeted to reach 30% of renewable energies in the energy consumption and 40% of RES generation in electricity by 2030. And in order to achieve these different targets, RT has created and participated in a document, strategic document called the PPE. PPE is the multi-annual energy plan. And in this plan, we defined our different priorities of public action. The first came in 2016, and every 5 years we update this plan. So it gives, what is the most important point is this plan gives target by technology for RES, for energy, for connection for storage and for each kind of connection, and set the government's strategic priorities. So storage, if you go in the multi-annual energy plan, we was a process in order to develop 1.5 gigawatt of additional pumped hydro storage for commissioning between 2030 and 2035. That's a mature technology, so I don't want to go in details about that. I will speak more about batteries because it's another question. We are working on the R&D division on some demonstration project in order to show the competitive use of the batteries. I will present in a few slides one of the projects called Ringo, and we'll show that the benefit that can offer storage capacity in order to solve congestion problem. And the last point is about the power to gas demonstrator, because it's so a storage capacity, and we have some we will have some demonstrators in France between 1 and 10 megawatts before 2023, and we hope to achieve 100 megawatts demonstrator before 2030. You go the next slide. In few words, the regulators, the French regulators, it's called CRE, want to set an ambitious roadmap for storage in order that the storage development becomes a reality in France. So the roadmap set by the French regulator for RT and the French different DSO concern the simplification of connection procedure, the treatment of mixed customer sites, the evolution of the grid demotioning methods, the market access rules that I will speak about just after this slide, and the publication of grid congestion in order to show to the stakeholders which are the location where it's be useful to invest on the network. So if you go to the next, I just look on the time. It's 3 p.m. so 1 hour, right? So I will go further and faster about the market access. That's one of the point, because we have the connection, the regulatory phase, but it's an important thing to speak about the market, because in order to push the investment and the connection of stakeholders on the network, you have to propose a very fair market for their investment. So storage can already participate to different market mechanisms. There are three kinds of market. The capacity mechanism, that's for the exchange power between the countries. Today is possible, and we offer simplified rules in order to which allow batteries to participating in frequency containment reserve mechanism, and in order to participate in the long-term tender. So that's one point. The second is about the FCR and FRR. So the two mechanisms in order to control frequency. So it's I call that ancillary services. And batteries can participate on this two mechanism. For FCR, that's the primary frequency control. Experimentation for batteries alone are ongoing, and AFRR is the automatic secondary frequency control in order to reach and to align the frequency to 50 Hertz. The experimentation for batteries alone is possible. We know technically that it's possible that batteries participate on FCR and FRR. So the last market offer is the Mfrr or on the RR is more on balancing mechanism, and it's like it's called the tertiary frequency control. It's a long-term control, so that's why I mentioned that it's only partial for eligibility of choice. And for batteries, it's more complicated to participate in this kind of mechanism because the time scaling is too much important. And if they want to participate in this kind of market, they need to sizing the batteries, and it can be a big impact on the cost. So only pumped hydro storage can fully participate on this market. To go on details about the different mechanism, if you go to the next slide. In order to participate on the capacity mechanism, the general principle is to submit our capacity allocation from a connection point, and then the value availability of units that can feed electricity into the grid from a connection point. And we propose two certification in order to allow this order to participate in the capacity mechanism. So I go further. The information on the slide, you can read that if you want, but don't go further due to the time. The second market access, if you go to the next slide, is about the FCR and the FRR. Today, the participation is possible through experimentation, as I mentioned before. But for the FCR, we have already several demonstrator and several owners of battery who are interested on that. On the question of FRR, this is limited today. And the last slide about the market access for a balancing mechanism. I mentioned already previously that it's more for the hydropower plants. There are different steps in order to participate in the Mfrr or RR. First is to introduce the storage capacity and the storage unit in the rules. And the storage is neither a power generation nor a consumer. So the first step is to introduce a proper definition in the rules. So that's a complicated step, but it's possible today. Then the step 2, it's about the full participation for storage. storage unit will be allowed to value simultaneously within and withdrawal, but will not be allowed to be aggregated with other units than storage units. It's a specific case for storage units specifically. And you have to know that there is an evolution of the rules for step 1 and step 2. I don't know. But I can give you more information in the futures about that. And step 3 about the storage integration in the Mfrr and the RR rules is about the opening of the opening and of opportunities to aggregate possibilities of storage. So to conclude this marketplace, as I mentioned at the beginning, there is today the different mechanism and different possibility for storage capacity to participate on market access. Here I mentioned what are existing in France on RT side, but we can develop that in Europe and well because this mechanism is valid on Europe. Important thing in order to facilitate the access of storage units on the transmission system operator networks. Before going on the next part, I will just have a small conclusion about that because here I present quickly the different how to connect a storage unit on the network, what are the rules and the legislation and regulation on storage, and you can see today that there are opportunities for storage capacity to connect on the network. The next part will be interesting things. Is about the technical question. If you go to the next slide, yes, storage can participate to the market, can connect to the network, but what are the other possibilities and what are the technical possibilities offered to the storage capacity in order to participate actively to the system, on the system stability or on different markets? That's the question. And if you go to the slide, it's a scheme provided by the European Association for Storage of Energy that I catch up. And there are different storage will play an important role today and in the futures. First of all, about on the generation case and the generation services, in order to support conventional generation, to participate on ancillary services, and for the power to X system. The second case is about ancillary services. And in my presentation, I will go in details about the primary frequency control and the frequency stability of weak rates. There are other services, as I mentioned, on the market opportunities, like the secondary frequency control and manual frequency reserve, the tertiary frequency control. You have to know that batteries have the opportunities to participate to the voltage control because they are connected directly behind power electronic devices. So here we have the different capacity can be offered by the storage capacity on our network. About the transmission systems, storage can support the network by solving the contingency and the congestion on our network. That's one of the tricky things that I will present just after. I don't go in detail, but we have the role of storage on the distribution services, and also for the customer energy management services in order to solve the peak shaving or composite reactive power or many other things that are mentioned in this in the last column. Okay, so if we go to the next slide. Okay. So that's a good question. Storage for which issues? Here I will mention one of the main points is about the grid congestion, and particularly about the localized congestion in the due to the topology of our network. Grid today has to absorb renewable generation unit connection, and both appear in time of high consumption or production. As you know, it's very difficult to build lines in a system to build overhead lines due to public complaints or other questions which are existing on this with new lines. So TSO cannot solve the congestion by traditional means that I mentioned, and this is the main risk for this the system operation, because if you have congestion, we need to cut off the line, and we cannot operate this safely our system. And in some cases, if you connect renewable energy in a point, we don't need new lines, because maybe the capacity of the line is 100 megawatts. Good. Next slide, please. And the generation unit can produce 130 megawatt, and the consumption is 130. Why do we need to build commissioning to insert a new line on this network? This scheme is very interesting. There is a patent from RT on this topic, but if you go further on this scheme, yes, today we have a line of 100 megawatts. It's just an example. We have an installation of 130 megawatt of renewable energies. So what we propose is to tell us that we don't need a new line. We can install in 2 points 2 batteries in order to absorb the generation unit production upper than 100 megawatts, and to provide this power in another place. RT or TSO cannot influencing and modify the equilibrium between production and between generation and consumption. And that's why we need to put 2 batteries, one to absorb, another to produce and to provide power. So with this scheme, we saw that the interesting opportunities offered by batteries. We don't need to build a new line. We can use only batteries to just pass the wave during event. So artists start a project about that called Ringo in order to automatically managing congestion. So we put only 2 batteries because it's difficult to operate and to solve these congestion issues and only with 2, but we will enter 4 batteries in 4 different places, and we will guarantee at each time that that we don't participate to the equilibrium between generation and consumption. And we could define an algorithm in order to optimize the absorption and the production of batteries. So if you go to the next slide, and we'll go in details about this automaton, how this control. So we install several batteries on the network. We will have a centralized, next slide, please. We will have a centralized automaton which will balance the energy within all batteries. The main objective of this algorithm is to maintain the power in order to absorb or to provide energy for the system at each moment. So based on the forecast file, so on the left side, we define the operational planning of batteries for dispatcher for the next 36 hours. The cost function is to add minimum level of renewable energy curtailment. It's an economical analysis. With these results, for each battery, so we balance in order to have the sum of the state of charge of the battery, which are constant, or the sum of energy. As I tell you that we cannot participate to the energy, we cannot influence on the energy. The sum of energy is equal to 0. That's the main algorithm. Then the output of this balance are used on the snapshot, in the snapshot fly, so for the operational procedure, for security analysis. And we can do the pre-positioning of batteries for the prevention. And a capacity bandwidth is provided, which is very useful to manage congestion. And on real time, the congestion is managed every 5 seconds. So if you go to this slide, the network optimization and calculation, I explain quickly how this algorithm was defined, and go in details. It's an optimization problem which is formed and solved with the battery based on the network equation, because we would like to avoid renewable energy curtailment or renewable energy curtailment. And the second point is the equation of energy. As I mentioned, we solve this optimization problem of several at each time step, and it's well known as a model predictive control. For the next slide, I feel that I've already mentioned this different point directly, but it's written in this on this slide, so if you want to read that, no problem. But I mentioned the centralized automaton is in charge of the network forecasting from 5 minutes to 36 hours. And it will send the instruction for local automaton. The main role of this centralized automaton is to balance the power of batteries. And the main objective is to guarantee that the sum of energy is equal to 0. And if you go to the slide directly 37, because we don't need to go further, it's an interesting scheme that you show that the operational distribution of this battery and the work. So in orange you have the maximal value that you can have on the line gray French line. Not useful to mention the name. So this is limited to 450 ampere. And we install battery on this substation. So it's in blue color. And we have in blue the different generation and load projection. And you can see that if we have an increase of production, we can see that the increase of current on the line. It's in blue color at the top. And when we reach the 440 ampere value, our algorithm works in order to absorb the energy by the storage capacity and to reduce the power on the line. And this is the way that this batteries works to solve congestion issues. So I don't know if it's clear, but what you have to understand is that the batteries are here in order to just solve the congestion issues. And when we reach the limit, the batteries worth in order to absorb the power. So that's the last slide about this Ringo project. It's a synthesis slide to show you that Ringo and this project is a smart combination of power and digital, and consider the important role of digitalization, because there are a lot of measure and there are a lot of working with automation and different level of automation in order to solve the issue on our networks. If you go to the next slide, here we will go directly on the dynamic application. I show the congestion issues are more static problem. Here we have. I will go further on details on dynamic application and more on frequency control frequency control, grid forming control, etc. So, where are there are different motivations to use batteries to participate on this dynamic application? Today, the main point is in the center. We observe with the massive integration of renewable energy or a rising need of provision of inertia. Inertia is not compulsory because inertia is a mechanical thing. But batteries or renewable energies can provide something similar the inertia, as I prefer called synchronism. It's one point. The second is about the frequency response. We need more frequency reserves in order to maintain our system stability. So batteries can participate to provide this service. And the last things that I mentioned on the left side is the frequency oscillation. I don't want to go on details on that, but we observe on the European network some low frequency oscillation, called inter-area oscillation. And we know that batteries or other systems can help in order to dampen this oscillation. So, go to this slide. The ESS are one way in order to improve system stability. So the first is for the inertia response, thanks to the fast frequency control, for example. The second is the classical frequency control, the primary frequency control. The third application is about the attenuation of system operation. And there are other utilities, like for the transient stability, ESS can participate during faults by providing negative reactive power current in order to maintain voltage at a certain level and avoid collapse. So on the next slide about the frequency containment process. It's just an example that I would like to show about continental Europe in a simple network and simulation with a system size of 150 gigawatt, and the inertia constant of 5 seconds, and the load reaction of 1%. This system is what we use on the European level, and it's for the policy one. And it's here to define the different rules, frequency rules in Europe, in continental Europe. We have a system with 150 gigawatt. We simulate a fault of 3 gigawatt, and we design the frequency control containment reserve. On network requirements, so the RFG, the requirement for generator, asks to system, generation unit or different system to react if frequency deviation is less than 2 seconds. The energy has to be fully activated when the variation is 200 millihertz. The time to activate, here it's in France, the time to activate the mid of the FCR is 15 seconds, the totally in 30 seconds. And each system has to guarantee 15 minutes the services. So it's an important value, 15 minutes, because if a system participates to the frequency control, they need to provide this system during 15 minutes. And this value is important to size the batteries and to compute between the power and the energy of the batteries. Here's in the next slide. Small figure to show how to participate in frequency control. The state of the charge, the SOC level, is very important, and that's what we need to maintain in a certain level in order to participate, of course, on frequency control. So if you have to participate 15 minutes for the frequency control, the state of charge of batteries need to be below the energy, the maximal energy, and the power that you offer for the capacity that you offer for the frequency control. So that I mentioned with the two equation, E minus RP multiplied by 25%, and SOC minus is equal to RP. So if you maintain your battery level between SOC minus and SOC plus, you guarantee to participate actively and correctly to the frequency control. And in continental Europe, we show that energy of the battery has to be equivalent to 1.2 of the primary reserve that you would like to provide to the system. This scheme is very important in order to understand that you need to allow a certain a certain range of power free to participate in frequency control. So you can use, a producer can use the battery between SOC minus and SOC plus, but never go further. Okay, next slide. So it's a Austrian Institute project that I take some elements in order to show you, and the Austrian TSO. It's a presentation that I thought many times, but it's something that we are easily understanding and we can apply. It's about the deterministic frequency deviation. Just to explain in a few words what is deterministic frequency deviation, we observe from several years, you maybe and surely the market truth and the early transit frequency variation at several hours when we change generation and consumption. As there is a step change each time, there are a lot of variation of frequency. And several times during the last years, we observed 100 millihertz or 150 millihertz of variation of frequency, which is very important for our system. So the role of batteries for this kind of event is that batteries can directly participate. It's like frequency control, can directly participate on the equilibrium between frequency, between generation and consumption, in order to
control the frequency. Why batteries? Because the time response of batteries is very, very fast. They can answer and they can provide a response in less than 1 or 2 seconds. So it's a very interesting product to maintain frequency in this on this range. So IIT and APG test several parameters for that during full hours, 5 minutes before and 10 minutes after. They push this regulation power. The maximum regulation power is when the frequency is more than 100 millihertz, and they put 1,000 on between 1,000 and 2,000 megawatts battery. So if you go to the next slide and the next. Here we have some results of Dfd products, and we can see here. We can go to the next slide. I go for a zoom on this. There are some in blue. We have the curve without regulation, without battery, and we have a frequency variation of 100 millihertz. If you go on the next slide, next, yeah, next. It's a zoom. For the next slide, I will zoom on the, yeah, here, perfect. In blue, we have the system without batteries and without regulation. The orange, 1,000 megawatt. In yellow, 1,500, and the powerful 2,000 megawatt. So can see that if you put a control on our system with batteries, we can reduce the impact of deterministic frequency deviation. It seems easier, but today for classical generation unit or renewable energy, it's very difficult to participate in a system very quickly. Yes, if you go to the next slide, so that's an example that I showed the utility of batteries. Next, we speak about the inertia reduction. There are two parts on that. One on the inertia reduction and the impact on system, and last is about the grid form. This simulation is based on the policy one that I explained before. It's a system with generation unit of 150 gigawatt of with an inertia constant of 5 seconds, and we simulate the loss of two unit, so 3 gigawatt loss. Typically, in our system, and the rules specify that the frequency cannot go below 49.2 hertz. This is the black curve with inertia to 5 seconds. With massive integration of renewable energy and power electronic devices, we will have less inertia on our system. And if you reduce the inertia, the rock-off and the first deviation will be more important. And that's what we can observe in this curve. And I don't know, here we simulate with an inertia constant with 2 seconds. We can show that the frequency reach the go below 49 hertz, where load shedding schemes are starting. So it's a critical value for our system. So we need to maintain the frequency above than 49.2. But with an inertia constant of 2 seconds, it's not possible. So the solution is the next slide, is to have a fast frequency response. We have a system we can react before less than 500 milliseconds. And here is the next slide. A few answer of that is we can see that with a system with batteries who participate on this control, we can reduce the drop of frequency. So it depends, of course, of power which participate on the frequency fast frequency control, but I don't go further on this explication because I know that the last presentation is about that, about fast frequency control. So I let my colleague present that. Then if we go to the next slide, okay, here it's about the grid forming control. And what is grid forming? Grid forming is a specific control defined on migrate project and other international projects in order to maintain our system stability and to participate to the synchronous in case of loss of inertia. I mentioned the Migrate and the Smoothie project because RT participates on that, and there are two European projects funded by the European Commission. You can find several all deliverables on the different websites that I mentioned on this slide. Next. So the question, why grid farming and why we need grid farming? Today, inverters are connected to the grid are grid following. This means that the renewable energies, the wind farm or panel, measure what happens on the networks, so measure frequency, and then provide power based on this frequency. So they need time in order to measure the frequency of our system. So synchronous generators create voltage and the frequency of our system. So if we have more renewable energy or no synchronous machine on our network, what happened? Because renewable energy cannot measure what happened on the network. So we need that some renewable energies or some inverters take the function to create the voltage and to create the frequency of our system. That's why we call that grid forming. Next slide. Yes. We can ask me that, what is the issue in Europe or about inertia? Because we are right today. We don't have issues with inertia, but in future, And if you analyze the TYNDP, so the 10-year network development plan scenarios defined by Hensoe, we can see that there are several times that we don't have enough inertia. The question is why grid forming and why fast frequency control is not sufficient. I can answer on that. Fast frequency control is a control where we use measures. So we need time to measure frequency in order to inject power on the system. But if the inertia decrease very fastly, and we can see on this figure that there are less than almost near zero inertia in the Great Britain, with zero inertia, the frequency will collapse quickly and very fastly and before 100 milliseconds. So we need something to maintain the voltage and the frequency, and that's the solution, the grid forming solution. Next slide. I mentioned the case of Great Britain, but another application case of grid forming is for in case of system split by Highland. You can have, for example, a system like European network, and if you lost the interconnection between France and Spain, the Iberian Peninsula can be totally alone and without inertia because there are already a lot of renewable energies. In this case, it will be very useful to have the grid forming function. So there are the two cases that I mentioned for why we need grid forming. First, in case of system split, in Highland, like Great Britain or Ireland or other small island, and in the future with the as we saw on the 10-year network development plan of Hensoe. So next slide. Okay, so there is different kind of converter which are connected directly to the renewable energy, and virtual voltage source converter as one of this kind. There is the current controls, one kind that is a typical one used by many generation units, and the VSC, the voltage converter, is one of the good candidate in order to be grid forming. In the Migrate project, we developed several. First of all, define what is grid forming and what we are expecting for voltage source converter inverter, voltage source converter, and we define different solution in order to be grid forming. So if you go to the next slide, so that I mentioned previously, on Migrate, we define what is the function that we are expecting for a grid forming. So to be a voltage source, to be perfectly synchronized, to provide energy and modify the energy function of the load,
And that are the different capacity that we are asking for the voltage source gate farming. And you know that there are some limits for physical for P-based system that I mentioned on the right side with the on red, particularly without the communication and the current of voltage source converter, because this is limited, very limited. So based on this constraint and on the definition that what we need for grid farming, we and several partners like Lille, Zurich, or Dublin define the converter. So if you go to the next slide, so I'm speaking. Next slide, please. Yeah, so next, yeah, I don't have enough time, so we go quickly. So we have we define different controls which are grid farming, and this here there is 3 controls, and they are open source, so we can if you want to know what is inside, it's possible. We can ask me and I can provide a link, and it's already on the Migrate website. And one is the filtered frequency drops, the other is a dispatchable virtual oscillator, another a matching control. So here we show 3 solutions, but there exist others. And we can see that this is a solution. This is a truly solution. And next slide. Next. Yeah. On Migrate project, we validate these different structures and different algorithm in order to see if this solution is operable and sufficient for system stability. And we test different conditions, and one of them that which we are testing and which is very interesting is to test the 3 algorithms on the same time with a network with inverter 1 is tuned with a first control, inverter 2 with another, and inverter 3 is the last. And what we show, which is the last slide, like the system, next slide, is robust in all cases. We simulate a short circuit near the first point of common coupling, and we can see that the system becomes on a stable condition operation at the end. And in small scale, yeah, all grid farming behave similarly. So it's very interesting because with several control, we show that it's possible to interoperate the system. And it's a good point in order to go further on the grid farming controls and to push manufacturers to install grid farming on their system. So we validate this different solution on laboratory, so it's on university lab. Today, the next slide, we are working on Osmosis project to have a real demonstrator on RTU website with a battery and a supercapacitor, and in order to show that grid farming can work in a real system. And today we install the material on the French on the RT substation, and next year we will start test to show this functionality. So next slide. So to few message about grid farming and the role can play by batteries, because on the last stream we showed that battery and supercapacitor can play this role. First of all, the grid farming function performance have been unified and defined from a system level perspective. So we have several algorithms and several solutions for grid farming, and all can be interoperable. The inertia level that we already mentioned that it's very important is not the unique solution. Batteries or all systems with all renewable systems connected via power electronic devices can participate. And for me, this year where we speak about storage capacity and battery, it's an important thing to show that batteries can help the system for for the stability and can participate by providing the grid farming function. So to conclude, let's go to the last slide. Here show the main role that can play by batteries. One is the balance, so to ensure the equilibrium between production and between generation and consumption, and that's the frequency control. The second is about the congestion usage that I showed with the Ringo project, in order not to invest on overhead lines, like that. And the last is flexibility with the grid farming function and etc. So ESS and R is and will be an important part of the network to support green transition. And I showed different utility for batteries, but we can mutualize that and provide multi-services with the same batteries. And as I mentioned, RT has been working for several years on new controls, the model predictive control for congestion, the grid farming, or the optimal use of energy system. Thanks for your attention. I am on time.
Perfectly on
Thank
time.
you.
Yeah.
So if you have questions, I don't know if you had the time, but my presentation was
actually,
maybe too long, but because I prepare for a long time, but 1 hour and a half is maybe not sufficient, but it's a good thing, because I feel that I can send the main messages on that.
Yeah. No, it is perfect. I would like to say your presentation is like travel in the future. It is what I feel. It's very exciting and even mesmerizing, I would say. It's absolutely perfect. There is one question actually from me. Could large scale PV plants be inertia provider?
So for inertia, you mean grid farming, I suppose?
No, fast frequency response.
Yeah. Large scale PV plant can provide the fast frequency control. maybe it depends on the architecture that we have, but for someone they need batteries, because in one side it's possible. It's they can reduce quickly the power. Provide more power is maybe too much complicated, but they can use batteries on this case. But yes, large-scale PV plants can be inertia provider, and it's one of the requirements for on the grid code RFG requirement for generator on the European the European level, and we ask for that synthetic inertia on the grid code and the specific article.
Okay, and then perhaps my second question is about VSC. You mentioned VSC as a good solution for grid forming.
Yeah.
In Med-TSO planning activity, we mainly consider new interconnection, and some of them, because of coursing C, for example, are HVDC, and why not VSC? How do you see the benefit or opportunity to give something like a bonus to interconnection VSC for future need in terms of grid farming?
Good question, and very good question, because I see that it's a very good opportunity to use the interconnection and HVDC in order to participate on system stability and to become grid farming, because HVDC is one of the main links and main power units on our system, because we can have 1 gigawatt or more than that for links. So yes, we have to think about that. Today we are discussing a lot in European level about that, because this is the aim of European Commission to connect 400 gigawatt offshore renewable energies. And if you want to connect these offshore renewable energies, you need HVDC. And for me, and that's one point that I push for several months, this HVDC can play a major role for system stability by becoming grid farming. So it's a good thing to analyze in the futures.
Thank you very much. Thank you very much. If no more question, I think there is no more question.
I have one question, but it's
yeah, please, Anas. Yeah,
it's among your experience and what and how you are seeing the future. Do batteries can in the future play the role of load shifting? Because now we know that as you mentioned in your last slide, they're used for the balance, they're used for frequency control and for solving some of infrastructure or grid problems, but not so much or not like pumped storage in terms of load shifting. Do you think that in the future it could be possible in one scenario?
I don't know. For the load shedding,
Load shifting.
Load shifting. Yeah, probably, but I don't analyze this point, so I cannot answer. But I feel yes, they can. In my point of view, batteries can offer several services And here I mentioned 3 services, but we can use that for other and more than that. And we have to study this different point. And the main question is not the capacity, I feel, but the economical point of view. We need to show the benefit in order to use batteries for the different services.
We have a last question from our colleagues from Cyprus Island. It's about grid forming. Question is: a power converter connected generation storage will be synchronized on the grid together with synchronous generator. As long as generation is less than the load, frequency will be falling. How does the grid forming function help with frequency stability?
Okay, good. Yeah, I see the question. You mentioned there is no source of extra energy behind the converter, but it's not totally right. I feel that if you need a grid forming, if we have the function grid forming, we need a buffer. And this buffer will help the system in order to maintain the frequency. But if generation is less than the load, of course, frequency will be falling. So we need extra energy. For the extra energy, is not just the question of grid forming, because grid forming is the first instant. We will maintain the system during the first instant. Then we need flexibility and reserve, margin reserves on the system. And here we have different solutions. So we can reduce load, or we can ask for batteries, large-scale batteries, in order to maintain the frequency. Just a point that would like to say, grid forming is here to create the synchronism and to maintain the system synchronism. It's not here to maintain the equilibrium during 10 or 1 minute. It's here at the first instant. And then if we don't have the equilibrium between generation and load, of course, the system will collapse.
Okay, thank you very much. And I think it is a good transition to the last presentation of today about fast reserve. And Marco, floor is yours.
Yes, I'm here. Good afternoon, everybody. So, just to introduce shortly myself, my name is Marco Pietrucci, and I'm the head of energy resources storage in the innovation factory team in Terna. Today, I'd like to share with you, next step, please. I'd like to share with you our experience in the energy storage field, and I will describe shortly our electricity system contest after our experience in energy storage, and for the last point, what we have designed in terms of new services to face the increasing of renewable sources. So, next, please. Okay, so this is just a little portrait of the Italian context. Please see the upper side of the chart. And just to share which is the situation in Italy, nowadays we have a percentage demand covered by renewable sources equal to 35%, 35. But in the next 10 years, our country has a specific target that put the goal to cover, talking just about electricity demand, put to cover the 55% of the demand with renewable sources. So it's a very high number. And just to talk about this kind of number, we are talking about just the average value of the year. So it means that there will be some hours where the Italy will be fully supplied by renewable sources. On the right of the chart, you can see another phenomena that we are seeing in Italy, that is the decommissioning of coal plants. So in the last 5 years, we have lost more or less 20 gigawatt of thermal production unit. And in the next 5 years, we will lose all the coal plant actually installed in Italy. So in the 2025, we will lose 7 gigawatt and 2 of power that actually is provided by coal plant. Next, please. This is the main impact that we expect with the increasing installation of renewable sources, and also to be aligned to the previous colleagues that was talking about the system inertia. One of the main impacts that we expect to have in Italy is some hours during the mid of the day, especially during the midday when the sun is very strong, where the system inertia is very, very low. So there will be some hours where the frequency will become not stable, and will be very, very difficult to contain the frequency drop. Next, please. Just to share some that I think that everyone can understand the picture on the chart, but just to share what does it mean by a TSO point of view, a decreasing of inertia. If I have a lot of inertia, so a lot of spinning machine, thermal plants, we have the situation that has been designed talking about the blue lines. So we have an event and we have a slope of frequency that is not very high. If the same event occurs with a very high level of renewable sources, we have the green line, and so we have in a few instances a very high drop of frequency, and we need sources to face this drop of frequency. Of course, we are not talking about the drop of frequency means the delta that we need to face, but we are talking about the speed related to the frequency drop. So what usually is called ROC-off, rate of change of frequency. This is the issues at the moment, or better, this is the issue in the next 10 years. Next, please. So this graph for me is really interesting. I'm referring to the right picture. So this is the answer of a coal plant compared to a gas turbine. So it means that if I have a frequency drop, a coal plant usually can provide more than 20 megawatt in less than 1 second. If we are talking rather than the answer of a gas plant, there is no contribution in the first 2 seconds. So it's a very much different for a TSO. If we are losing 8 gigawatt, 7 gigawatt of plants that can provide a very high power level in less than 1 second. And we will lose all these plants in the next 5 years. This is a big issue in Italy, and is a big and will have a great impact on the Italian grid. We will lose this very fast response that was ever provided by coal plant. We need to find something else that can provide the same answer and the same regulation in the first instance after an event. Next, please. Okay, thanks. So this was the scenario. What we are seeing now, and what we expect in the next 10 years. But we knew this scenario since several years, and for that reason, in 2012, we have started to design with our energy regulator some pilot project mainly related to the storage technology that have the specific goal to provide, let's say, mainly know-how, knowledge, and answer in terms of how many megawatt we can obtain by an energy storage system in which kind of time range. So how fast is storage technology, and also we have investigated also how much energy we can store in some energy storage plant in terms of course, grid services. So we have created two main projects. The first one that is on the right, that is called the Energy Intensive Project. And this was a project that was related to congestion management. So we have installed in the south of Italy, where when we have a lot of wind plants, and we have installed NAS technology, 35 megawatt for more than 240 megawatt hour. The other project that is called the Storage Lab on the left has a completely different goal. Here, the goal was to install and to test, validate several technology in order to understand which could be the services that I can ask to this kind of technology as TSO. So, next chart, please. This is actually our storage portfolio. So all the technology that Terna has installed, and that nowadays we are working in terms of the operation in real time. As I said before, we have installed NAS technology provided by NGK. We have tested flow batteries, Zebra batteries, five different technology of lithium technology. We have completed the last year the commissioning of a supercapacitor, and nowadays we are working to a new solution, new innovative solution that is based on the flywheel concept, but it's not a traditional flywheel, it's something more. Next, please. What we understood working with this kind of batteries for years. First of all, we have tested the aging behavior of the energy storage. As you can see in this chart, not all the technology has the same behavior if you are using the same cycle. So in this chart, you can see the blue lines that is called for the technology number 6. And we have tested this technology with two different cycles. The first one is a standard cycle, so full charge, full discharge in continuous way. The other one is a frequency regulation cycle. And you can see that this kind of technology has a different aging if you are referring to standard cycle, referring to frequency regulation cycle. So it's a technology with a very high aging if you have a lot of switching from charge and discharge. The technology number 5 instead, that is the red lines, it doesn't show a different aging if you are using for different purposes. So the aging seems to be the same if we are using for frequency regulation respect to a standard cycle. Next, please. This is just few results that we have obtained. This is not the whole result, but just a few screenshots, let's say. In this case, I'd like to share with you the testing that we have made talking about energy efficiency, the net efficiency of the energy storage system. So usually an energy storage system has a module efficiency higher than 95. If you are talking about the whole solution with inverter, auxiliary services, and so on, this level usually stays around 85%. But the real question is, which is the real efficiency value in the life, in the operating condition? So if we are referring to a primary frequency regulation, so a services where the battery have to be maintained on, you have to pay the auxiliary services, you have energy losses and so on, you are attending that there is a frequency drop. So in this case, the energy efficiency, of course, is very low. And you can see that the value is between 15 and 30%. Instead, if you are using the same system, not to provide just primary regulation, but for example, primary and secondary regulation, the results is completely different. In this case, we can reach an energy efficiency more or less equal to 70%. So, which means, which is the lesson learned, that if you have an energy storage, you have to use the energy storage as much as possible, not just for one service, but for more services. Next, please. This test is very nice. In this test, we have created a condition where we'd like to understand which is the best response, the fastest response of an energy storage just for activation. So it's not a regulation. We have asked to our energy storage system to go to at maximum power in charge or maximum power in discharge, and this is the results. So in this case, we have obtained from minus 100% up to reach 130%, so the full inversion power within a time that, if I remember well, was 80 milliseconds. So less than 100 milliseconds, we have switched from minus 100 to 130. So we have used also, let's say, an overload capacity of the energy storage system. Of course, this kind of application for a TSO can be very useful in case of defense system. So we have a grid event, we need to have a very fast response. I can ask to all my storage system to completely go in charge or completely go in discharge in less than 100 milliseconds. Next. So I've described which is the context, where we are going, and what we have done in the energy source field, what we have tested, what we have understood in terms of energy storage. Now we are working not on testing and validation, but we are working on the real life. So in the last 2-3 years, we have opened our ancillary service market to new services and new products. In Italy, up to 2070, only production unit can provide flexibility. So in the last 3 years, we have opened the market also to demand, also to aggregated units. And nowadays, we have qualified 1 gigawatt Mfrr of virtual aggregated units. So some aggregated units, very small, but that put together can reach the minimum level of 1 megawatt. The other product that we have created and that we are buying, let's say, because there is foreseen an auction within the year, is what we have called fast reserve, and this is the services that we have talking that we'd like to talk. Next, please. So, what is fast reserve? So, fast reserve is the answer to the cold decommissioning. So we have created products that need to support the grid in the first instances after a specific event. It's a regulation. It's a frequency regulation. It's not primary regulation. And is important. We are not talking about fast primary regulation. Is another job. Primary regulation has a time that is very long, because primary regulation in our Greek code is defined as a regulation that complete is full power within 30 seconds. And there is no limit, no constraints in terms of duration. In this case, fast reserve is a specific regulation that have to react within 1 second and have to support the system when just in the hour when the system has a very low level of inertia. So this is, let's say, the scope and how we have worked to design the services, the service fast reserve. Next, please. Another topic that is relevant for us, as a TSO, we have the goal to show our needs in terms of grid management, but we are not able to choose the technology. Of course, we need to know which could be the technology that can, let's say, can give a specific answer, a specific reply, but our tender are never technology agnostic. So fast reserve, in our opinion, is a services that can be well provided by energy storage system. But of course, if some aggregators thinks that it can provide the same answer with the demand response, it can qualify. There is no issues. If we are talking about distributed generation, is not an issue. Everyone can provide fast response. By a technical point of view, and I have to say the services is let's say, well fit on energy storage, of course. But we are just describing our needs in terms of grid management. Next, please. So the size. We have created this kind of tender, talking about a minimum size of the unit that have to provide the fast reserve, minimum size equal to 5 megawatt. And the maximum size is 25 megawatt. This is for two main reasons. The first one is to avoid that just one player wins all the megawatt that we have put in auction. The other one is that we are talking about the frequency regulation. So the best choice, but talking about the system operator point of view, is to have more sources that is redistributed on the land and that are not concentrated all in the same point. The maximum the maximum megawatt that we aim to install with the fast reserve is 230. So we are talking about 200 megawatt in the mainland, other 30 megawatt in Sardinia. Next, please. What we expect to have in the auction that, as I said before, we have scheduled within the end of the year, is there is a price cap equal to 80 kilo euro per megawatt. So this is the price cap, and all the participants, all the players have to bid something that obviously have to be less than 80 kilo euro per megawatt. This kind of value is a value that Terna has designed not for fully paid the plans. Our scope was to give something that pay enough of the capex and the opex of the player, but of course the player has to find other kind of revenues, because as I said before, the energy storage can provide more than one services, and actually can provide all the services that has been designed by a technical point of view in our Greek codes. So we need just to enable energy storage in providing all the services. But if we need energy storage, energy with a clear framework, energy storage can provide all the services. So good luck to the player. This is a good point to start and to have a plant that is is paid for a 30-40% more or less, the other on the market. Next, please. So, and as I say before, this is just our, let's say, the regulatory framework and the way that we have worked in the last year. So, it's all the design of the product was be designed with the operators, with the market and the players. So there was a public consultation. We have worked with our energy regulators, and now the goal is to make the auction within the end of the year. And after, there is 3 years that can be used to build the plans, and the first day of the delivery is the 1st January 2023. As I said before, the auction was designed to have a support in the hour where the inertia is very low. We are talking about 1,000 hours that Terna have to define and to communicate to the player 2 weeks before the real time. I think that is all. This is the main information that we'd like to share with you. So I hope that you have found of interest the presentation.
Thank you, Marco. I have a question from Emmanuel. You can read it in the chat. In the context of coal phase out, keeping alive a rotating machine only could contribute to voltage control and inertia provision. Do you think it could be matched with future needs and be a viable solution?
So yeah, of course. If we are talking about voltage control and inertia provision, if you have something that can spin and can provide a spinning reserve, is something that can be an answer. The goal that we have that we'd like to reach, of course, is regarding a decarbonization target. So in these terms, we are working to the decommissioning of coal and gas plant after. You have other solution, of course. Regarding the inertia and the voltage control, Terna has started to install 3 years ago synchronous compensator. We have installed 3, and now we are working on other 8 plants of synchronous compensator. There are storage. There are different technology that can support the energy transition in the hours where you don't have thermal production, and this is our goal. But it's correct.
Okay, thank you, Marco. Okay, Emmanuel.
Yeah, I think that there is no more question in the chat.
No.
Yeah, no more question. So I think we are perfectly on time. I think that it is time now to close the today conference. I would like to first thank a lot speakers and to emphasize quality of presentation. It was very, very nice. Today was, as I said, the travel in the future, and obviously the future is not. It's a very long future. It's perhaps not tomorrow morning, but very, very rapid. So very, 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 very important, very interesting. So now it's time to conclude those today, and I would like to conclude by giving you a rendezvous for a next step. I mean that we still have in mind to present more in detail storage technologies. And so it is a question. It is a question of finding the best speaker and to find time. And as soon as this program will be ready, I will keep you aware of that. So that is the end for today. I think that yes, info from the secretariat. I think it is a review. Yes, it is a questionnaire to know your feeling, your opinion about those 2-day programs. So please answer to improve quality step after step of those Med-TSO program. Thank you very much, and have a good day.
Thank you to everyone for attending the workshop. Thank you. Bye.
Thank you. Goodbye.
Thank you, everybody.
Bye, everyone.